The surprising success of dense solid-state qubits. New findings debunk previous wisdom that solid-state qubits need to be super dilute in an ultra-clean material to achieve long lifetimes. Instead, cram lots of rare earth ions into a crystal and some will form pairs that act as highly coherent qubits, shows a paper in Nature Physics. Clean lines and minimalism, or vintage shabby chic. It turns out that the same trends that occupy the world of interior design are important when it comes to designing the building blocks of quantum computers. How to make qubits that retain their quantum information long enough to be useful is one of the major barriers to practical quantum computing. It's widely accepted that the key to qubits with long lifetimes, or coherences, is cleanliness. Qubits lose quantum information through a process known as decoherence when they start to interact with their environment. So, conventional wisdom goes, keep them away from each other and from other disturbing influences and they'll hopefully survive a little longer. In practice, such a minimalistic approach to qubit design is problematic. Finding suitable ultra-pure materials is not easy. Furthermore, diluting qubits to the extreme makes scale-up of any resulting technology challenging. Now, surprising results from researchers at the Paul Scherrer Institute (PSI), ETH Zurich, and EPFL show how qubits with long lifetimes can exist in a cluttered environment, picking the gems from the junk. The researchers created solid-state qubits from the rare earth metal terbium, doped into crystals of yttrium lithium fluoride. They showed that within a crystal gem packed with rare earth ions were qubit gems with much longer coherences than would typically be expected in such a dense system. For a given density of qubits, we show that it's a much more effective strategy to throw in the rare earth ions and pick the gems from the junk, rather than trying to separate the individual ions from each other by dilution, explains Marcus Muller, whose theoretical explanations were essential to understanding bamboozling observations. Like classical bits that use 0 or 1 to store and process information, qubits also use systems that can exist in two states, albeit with the possibility of superpositions. When qubits are created from rare earth ions, typically a property of the individual ions such as the nuclear spin, which can point up or down, is used as this two-state system. Pairing up offers protection. The reason the team could have such success with a radically different approach is that, rather than being formed from single ions, their qubits are formed from strongly interacting pairs of ions. Instead of using the nuclear spin of single ions, the pairs form qubits based on superpositions of different electron shell states. Within the matrix of the crystal, only a few of the terbium ions form pairs. If you throw a lot of terbium into the crystal, by chance there are pairs of ions are qubits. These are relatively rare, so the qubits themselves are quite dilute, explains Adrian Beckert, lead author of the study. So why aren't these qubits disturbed by their messy environment? It turns out that these gems, by their physical properties, are shielded from the junk. Because they have a different characteristic energy at which they operate, they cannot exchange energy with the single terbium ions. In essence, they are blind to them. If you make an excitation on a single terbium, it can easily hop over to another terbium, causing decoherence, says Muller. However, if the excitation is on a terbium pair, its state is entangled, so it lives at a different energy and cannot hop over to the single terbiums. It'd have to find another pair, but it can't because the next one is a long distance away. Shining light on qubits.